AC circuit containing only capacitor. So this is my capacitor with capacitance C. I connect the two ends of the capacitor through an alternating source of EMF E equal E naught sine omega t. So this is my instantaneous EMF. So I'll name this as equation 1. Alright. Okay. Now, you know that when a source is connected to a capacitor, then a charge is transferred to the capacitor. Suppose at any instance of time t, see the charge which is given to the capacitor, let's say it is Q. So if Q is the charge of the capacitor at a time small t, then I can see here that this Q is equals to, this E is equals to Q upon C. Because we know right from the chapter of capacitor we have learned that V is equals to charge upon capacitance. Isn't it? Okay. So then instead of E naught, instead of E, I will write E naught sine omega t equal Q by C. Or just Q is equals to C times E naught sine omega t. So this is the charge at a time t which is given to the capacitor. Okay. Next, the current at that time t, it is usually written as, because we know current is equals to dq upon dt. Or this current I is equals to d dt of, instead of q I'll write c e naught sine omega t. Next, just I is equals to, taking common c and e naught, we take it outside the differentiation, then you differentiate only sine omega t. So when you differentiate sine omega t, you will get differentiation of sine omega t, it will be omega cos omega t. Okay. Or I can say here I is equals to E naught, I will write in this way, 1 upon omega c. And instead of cos omega t, I can write sine omega t plus pi by 2. Because sine omega t plus pi by 2 is again cos omega t. Okay. Now, let me write it here. I equal E naught. Now, instead of this 1 upon omega c, let's say I'll write xl. And then sine omega t plus pi by 2. Or I can say I is equals to, now this E naught is the EMF, XL behave like the resistance. So EMF by resistance is always equals to a current. And because the EMF is E naught, so the current also will be I naught. Okay. Okay. So you have to mention how much is XL, where XL in this case is equals to 1 upon omega c, and it is known as the capacitive reactant. So this capacitive reactant, it is like the resistance. So therefore I can say this capacitive reactant is the resistance which is offered by the capacitor. So it is measured in ohm. Okay. And this I naught here, it is equals to how much? E naught upon XL. And this is known as the maximum value of current. Alright. Okay. Looking at the two equations, this is equation 1 and this is equation 2. Now when you look at these two equations, you find that E equal E naught sine omega t, whereas I equal I naught sine omega t plus pi by 2. So because of this plus pi by 2, it means the current leads the EMF by an angle pi by 2. Okay, so therefore, when you represent the two waves using a phasor diagram, then if this is my current, this is my EMF, and the angle or the phase difference between the two is pi by 2. Okay, alright. So similarly, if you represent the two wave using a graph or graphically, if this is my EMF, then this would be the, yes. Okay, so if this is the EMF, then this is the current. Alright, okay. So please note down here that at this point, when the EMF is maximum, this angle is equals to pi by 2. This angle is equals to pi. This is 3 pi by 2. This is 2 pi, and so on. Okay. So this is the graphical representation, and this is the phasor diagram of the EMF and the current in case of a purely capacitive circuit. Okay. Okay, just make a correction. This is not XL, this is actually XC. For XL, we meant, inductive reactant, but for capacitive reactant, we write as XC. Okay. Now, after this, we will look at the special case. The special case is, number 1, for direct current. So for direct current, we know there is no frequency. That means F is 0. So when F is 0, this Xc, the capacitive reactant, which is equals to 1 upon omega C, I can write it as, instead of omega, I'll write 2 pi F times C, or because F is 0, so the denominator will be 0. So 1 upon 0 is equals to infinity. Okay. So this means that when a direct current is passing through the capacitor, then this capacitor, right, will offer a very infinite resistance to such a direct current. Or we can say the capacitor always block the direct current. Okay. Case number 2. For AC current, we know the frequency is equals to non-zero. And in such case, this Xc will always equals to 1 upon omega C, which means 1 upon 2 pi F times C. Okay. Now, because this F is non-zero, then depending upon F, when F is large, Xc is small. When F is small, Xc is large. Or in other words, I can say, when an alternating current with large frequency is passing through the capacitor, then this capacitor will offer less resistance to such current. However, if a current with small frequency is passing through the capacitor, so with small frequency, then what happens to Xc? Xc will be large, which means when a current with small frequency is passing through the capacitor, then this capacitor will offer a very large resistance to the AC circuit. Alright.